arrived?
No, we haven't. We've had to land because we have a slight problem with cosmic dust contamination in the water that our engine uses for fuel. This is due to our encounter with that last asteroid.
Let's have a look around, see where we are. Interesting. We seem to have landed at a place called Alfa-laval on the planet Earth. Okay, I've seen enough. Let's remove the dust from the water and go.
I'm afraid we can't without help. That's why I steered the ship here, where such technology does exist.
What technology is this? I don't know anything about it. How does it work?
Don't be concerned. I will answer all your questions for you.
Tell me then, how do we remove the dust impurities from the water?
Well, this is a case of separating solids from liquids, a process that uses gravity. We don't really understand what gravity is, but we do know what it does. If, for example, dirty water is left to stand for a time, it will clean itself. The heavier solid particles, the dirt, sink to the bottom, and the water above is then clear.
Okay, but what's really happening?
Look at it this way. If the blue globules represent the water, in this case the lightweight component, and the brown particles are the dirt, in this case the heavy solids, then, once all the solids have settled to the bottom, separation is complete. This process is called batch settling. The clear water can then be collected by pouring it carefully over the edge by decanting it. There are two major factors that influence the efficiency of the separation process. One is the time allowed. The other is gravity, or, more precisely, gravitational acceleration. The time required to complete the settling process efficiently depends, in turn, on two other factors. Firstly, the settling velocity of the particles, and secondly, the distance they have to travel.
That's all very well, but how can I use these factors to speed up the process?
Right. To make the settling process faster, we need to reduce the distance particles have to travel. We do this by making the vessel shallower.
What, like this?
Yes, but we need to keep the same volume. So what else can we do?
We can make the vessel wider.
Yes. Now, by adding an inlet and an outlet, we can arrange for what is called continuous flow. In other words, the mixture is fed into the tank at one end, and the lightweight component, in this case water, is discharged at the other. The particles then move in two directions, vertically downwards because of the pull of gravity, and horizontally due to the flow of the liquid. If everything's correctly dimensioned, all the solid particles will settle at the bottom, and the clean liquid will be discharged through the outlet. So, if we increase the rate of flow, what problems do you think we might have?
I don't know.
Well, some of the solids may not have time to reach the bottom, so they'll flow out through the outlet and the liquid won't be clean.
So, how can we speed up the process without this happening?
We can insert a shallow tray. This will reduce the settling distance and therefore the time required. How do you think we can take this a step further and make it even more efficient?
Have more trays. We could insert several close together. The result will be a better separation and faster too.
Yes, that's exactly what it does.
That's great, but we are lucky it was only dirt in the water. I guess we'd have been in real trouble if it had been oil.
No, that's not true. We can also use gravity to separate immiscible liquids, like a mixture of oil and water. In a U-tube, the lighter liquid, the oil, is pushed upwards by the heavier one, the water. If we try to separate them in a simple batch settling tank, what do you think we could expect to find after some time?
It looks like we have 3 layers. A clear layer of oil on the top, a narrow layer in between of still unseparated mixture, and on the bottom the heaviest layer, water.
Exactly. We call the clear layer, in this case oil, the light phase. The thin emulsion layer of unseparated mixture between the two we call the interface. and the water on the bottom is called the heavy phase. Now, what will happen if these are left standing for much longer?
The interface gradually disappears and is replaced by a very thin diffused belt of the two liquids.
Yes. Now, remembering the case of separating solids from the water, how do you think this process could be made into a continuous flow?
If we give the tank an inlet and an outlet for each liquid, the feed will then pass continuously under the baffle to form an interface. The light phase then rises to the top outlet, and the heavy phase sinks to the bottom outlet.
Ah, yes. But how can we balance the system and keep the interface level where we want it?
Can we do it by varying the pressure in the lower outlet?
Yes. This is called the balanced column or U-tube principle. We can now separate immiscible liquids such as oil and water continuously. The mixture is fed constantly through the inlet section, after which it passes under the first baffle and on into the tank where it forms the interface. The light phase then rises to the top outlet. The heavy phase sinks towards the bottom and is discharged through the lower outlet. So far, so good. But how can we improve the tank so as to make it adjustable for other immiscible liquids of different densities?
We could provide the lower outlet with a weir or dam to effectively adjust the height of the outlet and hence the back pressure.
Exactly. But what would happen if the dam is set too low?
The position of the interface moves lower, which means there will be a risk of some of the light phase escaping with the heavy phase.
And if it is set too high?
The opposite will happen, and some of the heavy phase may escape with the light phase.
Very good. Now let's go back and see how we would express the whole thing mathematically. We call the settling velocity of the heavy phase particles or globules V. S is the density of the heavy phase particles or globules, and the density of the light phase globules is S1. We call the diameter of the heavy phase particles D, and the gravitational acceleration is called G. The viscosity of the lighter phase, the liquid, we call mu. When all of these factors are combined, this is what the formula looks like.
That's fine as far as it goes. But is there anything here we can use to speed up the settling process even further? Can we increase the size of the particles?
Sometimes, but only slightly.
What about the densities?
Unalterable, I'm afraid.
What about the viscosity of the lighter liquid?
Well, heating a viscous oil will make it thinner, so that could help a little, I suppose. Sorry, you can't change that.
What about G? Surely that's constant.
Gravity is, yes. But you can replace gravity with centrifugal force, and so multiply G by thousands of times.
Can you really?
Yes, this is called Stokes' law. By turning the process in the tank on its side and spinning it, centrifugal force replaces gravitational force and greatly increases it. So now we have what's called the bowl of a centrifugal separator, rotating at around 5,000 revolutions per minute.
Oh, that's great. But look, as the speed increases, some of the lighter globules are escaping along with the heavier liquid, even though the bulk of the liquid is clean. How do I capture the loose, lighter globules and control the interface, keeping it where we want it?
Remember the dam or weir in our balanced column tank? How do you think we could adapt it to fit the bowl?
Because the tank is now a bowl, the dam must become a ring.
Precisely. This is called a gravity disk, a sort of restricting ring by which we can control the position of the interface. A smaller inner diameter in the disk moves the interface towards the center. A larger inner diameter moves it outwards. Now, what happened before when we tried to increase the rate of feed?
There wasn't enough time for separation to take place, so a large proportion of the oil will still be carried out with the water. But when we encountered the same problem before, we solved it by inserting a series of shallow trays. You remember? Can we adapt this principle to the bowl?
Yes, by turning the trays into cylinders inside the bowl. This greatly improves separation efficiency. Another question for you. What will happen to the particles nearer the center of rotation?
They'd be subjected to a smaller, less effective centrifugal force, wouldn't they?
Yes. So could we compensate for this in the shape of the cylinders?
We could turn them into conical discs and alter the shape of the bowl accordingly. This will make them more effective and also allow the particles to slide in the direction they have to travel.
Yes, a simple but important idea. This is what is called a disc stack. The final improvement is to put holes in the discs in the region of the interface to speed up the liquid flow. So, by turning the dam from the balanced column tank into a ring or gravity disc, we can control the position of the neutral zone in the bowl. By turning the trays into conical discs or a disc stack, we have compensated for the smaller centrifugal force nearer the center of the rotation, and we've allowed the liquids to flow more freely. Finally, by making holes in the discs, we've improved the efficiency even more. The bowl is the most important part of the separator. If we then fit a drive unit and a cover, the result is a centrifugal separator.
So this is a typical separator?
Yes, but there are three main types of bowl available. First, we have the solid bowl centrifugal separator that we have already seen. It has a solid wall with no outlets. This type is a solids retaining separator and is used for what is known as intermittent service. In other words, at the end of each run, the bowl hood is removed and any compacted solids are lifted out manually. This is the basic type, and it is used for liquids containing a low percentage of solids, up to 1%. Products like explosives, edible oils, soap, and rubber or latex. The bowl may also be made solid ejecting, that is, of the self-cleaning type. The separated solids that accumulate in the sludge space of the bowl are ejected by centrifugal force. At certain intervals, discharge ports around the periphery are uncovered for a fraction of a second. These are known as PX separators, and they are used for liquids with a higher solids content, up to 10%, or when we don't want to stop the machine for emptying. It's used for fuel and lubricating oils, milk, wine or beer, fruit juice, and radioactive wastewater. In the nozzle separator, the solids escape continuously through the nozzles around the bowl periphery. With this system, the solids may be recycled for further concentration. In some cases, the solid itself is being recovered. The liquid is the byproduct. This type of separator is used for suspensions that contain larger quantities of solids, between 10 and 25%, like yeast, alcohols, starch, palm oil, or synthetic fuels. A fourth type of separator, known as a decanter centrifuge, can handle liquids containing as much as 40% solids. This machine differs from the separators we have already looked at in two main aspects. Firstly, it rotates horizontally instead of vertically. And secondly, there is no disc stack. The separated solids are discharged by a screw conveyor that rotates within the drum. Because of its large capacity for dewatering sludge, a decanter centrifuge is a useful machine for treating products that are to be subsequently dried, such as meat byproducts, sewage dewatering, plastics, and for fish processing.
Oh, so there are four types of separators. Solids retaining, solids ejecting, nozzle separators and decanters. And they can handle between 1 and 40% solids in a liquid.
Yes, this is the technology available in centrifugal separators today. Things have come a long way since Gustave de Laval invented the centrifugal separator in 1878 and founded the Alfa-laval company shortly after. Centrifugal separators are now used for concentrating, recovering, clarifying, and cleaning processes in foodstuffs, chemical, oil, pharmacy, and beverages. And another thing, you will find Alfa-laval separators in over 60% of all ships afloat today. Research and development continues. New fields are being constantly discovered where conventional methods can be speeded up and made more economical by the use of centrifugal separators.
Good. Right then, having used the separator to remove the impurities from our fuel, can we get going now?
Certainly. I will just replot our course from here and prepare for space transit.
By the way, do you think we could install one of these separators in the spaceship, just in case we have this problem again?
I'm sure we can. Okay, I've ordered one. We'll pick it up on our next visit.